Hi, welcome back to the second part of the lecture on data refinement. In this part, we'll be seeing a couple of examples on this subject. Our first example presents a data refinement in which we remove irrelevant information. This machine records the marks of each candidate in exam. It has three operations. We can enter the mark of a given candidate, we can return the average of the marks, and we can return the number of marks inserted. Let's see. So, our abstract machine exam has a set called candidate. This is a deferred set, so we don't declare the values that are part of this set right now. And we have a function, a variable called marks, which is a function from candidate, a partial function from candidate to the marks. And we initially have no elements in that function. So we can now enter the mark of a given candidate, we can ask the average of marks, and we can ask the number of marks inserted. So to enter a candidate mark, we receive the candidate, and that candidate cannot be part of the domain, it cannot be a member of the domain of marks, so it's a new candidate. It's a candidate that has not, to which we have not yet assigned a mark. And we get a mark, an n, which is a number belonging to the set ranging from 0 to 100. And we simply assign marks of CC, applied to CC, to that mark. So we simply include the pair CC and n to the function marks. To get the average of the marks included, we must have some mark already, so the function marks cannot be the empty set. And what we do is that we simply return the division of the sum of all marks with the number of marks inserted. To get the sum of all marks, we use the sigma function. This is a function that Atelier B provides, the B method provides. So the sigma function is the summation of all z's belonging to the domain of marks, and we sum the value of the mark of that z. So we are basically summing all the marks of all candidates, and so that expression gives us that value. And we divide that by the number of marks included. So we get the domain of the marks, those are the candidates, the set of candidates, and we get the cardinality of that set. So that gives us the number of marks that have been included. So by dividing the summation, the sum of all marks, by the number of marks, we have the average of the marks. Finally, we can return the number of marks inserted, and as we saw in the average operation, that's given by this expression, which gives us the cardinality of the setting containing all candidates to which we have assigned a mark. So after initializing this machine, we can, for example, say that the candidate 1 has mark 1, the candidate 3 has mark 2, and the candidate, let's say, 2 has mark 7. And now, if we want the average, it's a natural number, that's the division, resulting from the division of 10 by 3. So that's 3, and we have included 3 marks. And that completes the presentation of the abstract machine exam. A possible refinement of the machine exam only needs to maintain the information needed to give the appropriate information of the output operations. This has nothing to do with the individual marks of each candidate, but only with their average and quantity. It's important to notice that the refinement implicitly considers the precondition that the red guarantees that only new marks are inserted. Our refinement will present a new constructor, sequential composition. The sequential composition S, semicolon T, behaves as we would expect. T is executed from the state resulting from the execution of S, and the whole command succeeds only if both commands succeed. We may combine any number of commands in sequence. For example, we can have the sequence of two assignments, x receiving x plus 2 and x receiving x plus 4. As expected, at the end, the value of x will be increased by 6. We can also have another assignment, for example, y receiving x plus y and x receiving y minus x. And finally, we can have a swap with 3 assignments in which the variable t receives the value of x, and then the value of x receives the value of y, and finally the value of y receives the value of t. So let us now see the specification of the refinement exam R that refines the abstract machine exam. It has only 2 variables, total and num. Total stores the sum of all marks that are included. And as we saw in the specification of the abstract machine, this is given by this expression that uses the sigma function. The other variable, num, stores the number of marks that have been included. And as we also saw in the specification of this abstract machine, this is given by this expression, in which we take the cardinality of the set of the domain of marks. These are the set of all candidates to which we have included a mark. We start both variables with the zero, with the value 0, so total receives 0 and num receives 0 in the initialization. And to enter a mark of a candidate CC and NN, we simply add that mark to the total, and we increment the number, the variable num, by 1. The average simply returns the division, the integer, the natural division of total by num, and the operation num simply returns the value that is stored in the variable num. It's important to notice that the precondition of average in the abstract level says that marks is different from 0, or from the empty set. That means that we will not have a division by 0, because as we must have included at least 1 mark, num will be greater than 0. The precondition of the operation enter says that CC is not in the domain of marks, and that guarantees that we will not be overwriting marks. So that guarantees, that makes the whole machine work. And that completes the presentation of the refinement component exam R. Regarding the inheritance of static information, we have that refinements have access to all static parts of the abstract machine and of the machines it includes. We also have that refinements do not have access to machines that the abstract machine sees or uses. And finally, refinements do not have access to the value of the state of the abstract machine while it's executing. Our next example illustrates these characteristics of the refinement machines. This machine records a pile of items that need to be ironed. It has 3 operations. We can put an item in the pile, we can take an item from the pile, and we can carry if a given item is on the pile. Let's see this specification. Let's see the abstract machine ironing using ProB. So abstract machine ironing has a constant called limit, which is a natural number greater than 0. It also has a deferred set called item that represents the items of the pile. And the pile is modeled as a variable called pile, which is a sequence of items. But the size of this pile has to be less or equal the limit. So limit is a constant that gives us the maximum number of items in the pile. We initialize our pile with the empty sequence, and we can put elements on the pile, take elements from the pile, and query if an item is on the pile. So to put an element, we receive an item, II, and to To be able to put an item, the size of the pile has to be less than the limit. In that case, we simply append that item to the end of the pile. To take an item from the pile has to be non-empty. So the precondition of the operation take says that the pile has to be different than empty. And what we do is that we keep the front of the pile in the variable pile, and we assign to the output ii the last element of the sequence, so the last of pile. Finally, to query if an item is in the pile, we simply we receive an item, and we simply return the Boolean value that says that if an ii, the given item ii, is in the range of the pile. So let's suppose we have that that our pile is initialized with the limit being 4, so it can have 4 elements, 4 items in the pile. So after initializing the pile, we can put items to it. So we can put item 1, for example, twice, item 3, and item 2. And as we see, we have already put 4 items in the pile. So you can see here in the left-hand side. So we have reached our limit. So we are no longer able to put elements to the pile. If we ask if item 1 is in the pile, it's true, as it is for item 3 and item 2. But notice that for item 4 and item 5, the answer will be false because these items are not in the pile. So the last element included in the pile was item 2. That's the reason why if we take an element from the pile, the answer, as we can see here in the history, will be item 2. The next item to be taken will be item 3, and then twice item 1. Now our pile is empty, and as we can see, we can no longer take elements from the pile because there are no elements in the pile to be taken. Now, we can refine that as a refinement component, ironing R, that refines iron, but has 2 variables, an array called pile array and a counter. It has a constant EE that is an item, and our pile R variable is an array of limit elements. So we have an array of size limit, and it's an array of items. Our counter counts the number of elements in the pile, and it's a value that ranges from 0 to limit. So our counter is actually the size of the pile. So our concrete variable counter equals the size of the abstract variable pile. And the pile is the array that represents the pile is the abstract variable, and its value equals our array, but our array only ranging from the 1 to counter. So we initialize our array with all elements being our constant EE that actually represents a dummy item, and our counter is 0. So actually, if we look at the linking invariant, that is by setting counter to 0, we're saying that our pile is empty. So to put an item to the pile, we simply set the element at index counter in the array to be the new item ii, and we increase our counter. To take an element from the array, we decrease our counter and give as output the element at the new value of the counter at the decreased value of the counter in the array. Finally, to query if an element is in the array, we check again if the element is in the relational image of the pile array to the set 0 to counter -1. If it is in there, the answer will be true. Otherwise, the answer will be false. It's important to notice here that the refinement component has access to the constant limit, to the set item, and to the variable limit. Those are all elements coming from the abstract machine. And as we see here, the refinement ironing R has access to all these components. And that finishes the presentation of the refinement of the ironing machine. Refinements can only contain, as we see, includes, extends, promotes, and cease. That means that refinement machines can be extended or included, and operations can be promoted in refinements in the same way as in abstract machines. Abstract machines can be seen in refinements. And finally, that uses cannot be used in refinements. Furthermore, refinement invariant links its state, and of machine it includes and extends, to that of the abstract machine. We also have that states of these machines can be used in operations. And finally, that includes machines. State cannot be updated by the refinement, but only by machine operation included. Our final example illustrates these concepts. It describes a machine that records information of a port. Basically, it keeps track of the ships that are waiting to be docked, and also keeps track of the docks and the ships that are using them, if any. We have 4 operations. We can register that a ship has arrived and put it in the waiting queue. We can locate a given dock to the first ship of the waiting queue. We can register that a given ship has left its dock, and we can return the number of ships that are waiting for a dock. So let's suppose we have 5 ships, ship 1 to ship 5, and that these 5 ships arrive. If we ask the number of ships that are waiting, we have 5 as an answer. Now, let's dock ship 1 to quay 5, let's dock ship 2 to quay 4, and let's dock ship 3 to quay 3. If we now ask the number of ships that are waiting in the waiting queue, we have 2 as an answer. Now let's suppose ship 1 leaves quay 5 and returns to the ocean. Notice that it now is enabled to arrive again. Finally, let's dock ship 4 to quay 5. And let's dock ship 5 to quay 1. And that's the situation we have. And now, let's suppose all ships leave the dock and notice that all ships are back into the ocean and they can arrive again. Let's now see the specification of the port at the abstract level. Now, let's see the specification of the machine port. This machine has 2 sets. The set represents the ships and the set representing the quays. Both are deferred sets, so they will be valued at some point later in the development. And it has 2 variables. A variable waiting, that's an injective sequence of ships, and the variable docked, that is a partial injective function from quays to ships. And by being injective, that says that we cannot have the same ship twice being mapped by 2 different quays. We cannot, the ship can be only docked at 1 quay. And of course, the range of the waiting sequence is completely different from the range of docked ships. So the intersection between the range of the waiting variable with the range of the docked variable must be empty. We initially have that the waiting list is empty and we have no ships being docked. So waiting receives the empty sequence and docked receives the empty set. When a ship arrives, we receive SS, a ship, and this ship cannot be waiting, so SS is not a member of the range of waiting, and this ship can also not be docked, so SS is also not a member of the range of docked. and we simply include SS to the end of the list, to the end of the sequence. To dock, we receive QQ, a query, but to dock, we must have ships waiting. So the waiting sequence cannot be empty, and we receive this query, QQ, and the query must be empty. So QQ cannot be a member of the domain of docked. So in that sense, we will dock the first ship in the waiting list to that empty dock. So the waiting list is updated to the tail of its current value, waiting. And the first element of the waiting list is the ship in the front of the queue becomes is docked to that dock QQ. So docked of QQ becomes that ship, the first of waiting. When we say that the ship SS is leaving the dock, we must give it a ship that is docked. So we must provide an SS that is a ship, and SS must be a member of the range of docked. So what we want to give as an output is the query to which the ship was docked. So QQ becomes is assigned the value of the inverse function docked applied to SS. So if we see the function here in the top, we get a ship, and as it is an injective function, the inverse will be also a function, and we will receive the query that was mapped to that ship. And this will be given as output QQ. And docked, the docked function, we remove the pair that maps the query that was given as output to the ship that was given as input to this operation. So we make a range anti-restriction on the set SS, on the set containing the given ship. So we'll remove the pair QQSS from the function docked. Finally, to return the number of ships that are waiting, we simply return the size of the queue. We simply return the size of the variable waiting. So now we can animate this machine. We initialize it, and we can see that there are no ships waiting, there are no ships to be docked. And let's say that ships 1 to 5 arrived exactly at this order, ship 1, 2, 3, and 5. And as we can see here, we have a queue in which ship 1 is the first one and ship 5 is the last one. If we ask the number of waiting ships, we have the answer 5. And now let's dock ship 1 to queue 5. So if I dock queue 5, it will dock the first ship in the queue, that is ship 1 to queue 5. Let's dock ship 2, which is now the first element in the queue because ship 1 has already been moved to queue 5. So if I dock queue 4, that will dock ship 2 to queue 4. As you can see here, queue 4, docked of queue 4 is ship 2. And let's dock to queue 3, and that will make the docked of queue 3 become ship 3. Now if we ask the number of waiting, we have 2. Those are the 2 ships that are waiting in the queue. Let's say now that ship 1 leaves. If we say that ship 1 leaves, we get as output queue 5, as you can see here in the right hand side. And notice that ship 1 returned to the ocean, so we can actually now again say that ship 1 arrived. Now let's dock the next ship in the waiting list to queue 5, and that is ship 4. So docked of queue 5 becomes ship 4. And let's dock to queue 1 the next element, and that is ship 5. So docked of queue 1 becomes ship 5. So in this situation we have ship 1 at somewhere in the ocean waiting to arrive. We have no ships waiting, and we have 4 ships docked. Now let's say that all ships leave, and we are back in the initial situation in which all ships are at some point in the ocean. We have no ships waiting, we have no ships docked. And that completes the presentation of the abstract machine port. A possible refinement of this machine can use 2 other machines. A machine list describing a FIFO queue that is used to describe a waiting list, and a machine map describing a function that is used to map queries to ships. Let's see these 2 machines. So our list machine is very simple and describes a FIFO queue. As you can see here, the machine list receives a set of elements. Those are the elements that are in the queue. And this list can be defined as a sequence of elements which is initially empty, and we can simply add elements to it or take elements from it. So to add an element, we receive an element and append that element to the end of the queue, to the end of the sequence. And to take an element, we can only invoke that operation if the list is not empty, and we have that the list becomes the tail of the list, and the first element of the list is given as output. The other machine, the map machine, describes a function that is used to map, that will be used to map queries to ships. So it's basically a mapping from some index to some sort of items. And it has a function, fun, that's a partial function from the index to the items. This function is initially empty, and we can simply insert pairs, remove elements, remove pairs, or query what's the value of the function to a given element. So to insert elements, we receive an element SS1 from the type of the index, and an element SS2 from the type of the item, and we simply say that the mapping of the function of SS1 equals SS2. To remove the mappings from SS1, we receive some element of the index, of the type of the index, and we use domain anti-restriction to remove all pairs from the function in which the first element is SS1. Finally, to query the value of the function to a given element of the index, we must receive some SS1 that belongs to the domain of the function, and we simply return as an output the application of that function to that element. So we return the element to which SS1 is mapped. And that completes the presentation of the abstract machine list and map. Our refinement, we use another concrete construct, the variable block. The variable block var t in s and also behaves as we would expect. It declares a local variable t. The scope of the newly declared variable t is s. However, s must assign some value to t before using it. For example, let's suppose we have a variable block, as we can see in the screen, that declares a variable t and then makes the swap command, assigning x to t and then y to x and finally t to y. We may also declare many local variables in the same block. For example, we can have a variable block declaring 2 variables, x and y, and then executing the command s. This block, of course, declares 2 variables, x and y. Let us now use variable blocks and sequential composition to provide, using the machine's list and map, a refinement of our machine port. The refinement port R refines the abstract machine port and includes 2 machines, a list of ships and a map from ship to query. It has 1 variable, none, and the invariant says that the waiting variable of the abstract machine port equals the list variable of the included machine list. Also, that our function of the map machine equals the inverse of the function docked of the port machine. And finally, that the variable num equals the size of the waiting variable of the machine port. We initialize num with 0, and then we have the operations. First, when a ship SS arrives, we add this ship to the list of ships, and we simply increase the variable num by 1. When we want to dock a given dock QQ, we use the variable block to declare a variable sh, and then we take the first element of the list and assign that to this local variable sh. And then we insert a map from sh to the given dock QQ. Finally, we decrease num by 1 because we have removed a ship from the waiting list. The next operation, leave, models when a ship leaves its dock. So we query the dock of that ship and assign that to the output variable QQ, and we remove SS from the map. The operation number waiting returns the number of ships that are waiting in the waiting queue, which has been stored in the variable num. And that's all for this lecture on data refinement. I hope you enjoyed it. See you in the next one. Bye.